people can ask questions this afternoon.
Thank you very much. So there's not much to say since we are all pretty much experts by now in these informal discussions. However, I do want to thank Malena and Tiago. Malena designed the website that many are saying is the most beautiful strings website ever, and I agree. And Tiago is making sure that all the PDFs are posted timely, updated, all the videos are always online. And that's super convenient, in particular for this discussion. So Sabrina's video and PDF are already online, say. And so I would like to propose a big thank you to Malena and Tiago. And then, without further ado, Andy and Tomasz, you know the rules, 20 minutes, followed by 30 minutes, and this 30 is 30 plus minus something, plus something, of a relaxed discussion. So please, I don't know who goes first, if Andy or Tomasz, take it away.
Okay, well, since you were thanking everybody else but yourself, let me thank you and Nathan for this fun and different workshop. So I'm not gonna review celestial holography. I'm just gonna look to the future, and I'm gonna present what I think of as a greedy wish list of things that we might get in the next 5 years. None of these are cats in the bag, but they're problems that we hope to address in the next 5 years in this program of celestial holography. Now, just 30 seconds for those of you, especially in California, who was 5:30 in the morning, who missed Sabrina's excellent review talk. The basic idea of celestial holography is that you rewrite the S matrix for 4-dimensional scattering in quantum gravity as a correlation function of a celestial conformal field theory on the sphere, and this celestial sphere sits up here at null infinity. And this would be a theory without gravity. This would be a theory with gravity. And there's a holographic dictionary, which Sabrina reviewed an awful lot of during her review this morning. But I'm not going to review any of that. I'm going to just talk about what we might hope for in the next 5 years. What are the problems that we could hope to solve? And so one of them is to find all the non-trivial symmetries, the ones that have measurable physical consequences, of the laws of physics that we've known, GR for 100 years, and the standard model for 50 years, in the approximation where there's no cosmological constant. If there's a cosmological constant, we have to worry about de Sitter, whatever. Okay, so we're just imagining we're working in the approximation where space is flat. Now, these symmetries include the antipodal subgroup of BMS acting on the future and BMS acting on the fact. This is past. This is a particular set of super translations plus Lorentz transformations, but it's become clear in the last 5 years that this is only the beginning, that this is already an infinite number of symmetries, but it's become clear that there's an infinite power of symmetries that generalize this. And these symmetries have physical measurable consequences. They're non-trivial symmetries that act on the S matrix in a non-trivial way. And we don't know what they are. And I would say that, we theorists are behind on our homework. This isn't new laws of physics. We don't need experimentalists can't help us with this problem. They've already given us all the information we could possibly want. We have the laws of physics, and we don't understand what their consequences are, in some cases, very direct experimental consequences. Now, and it turns out to be a really surprising, it's surprising that we haven't solved this problem in 50 years. It's also surprising what an incredibly subtle problem it is. And there are many equivalent formalisms to address this problem. Hamiltonian approach, asymptotic symmetries, symmetries of the S matrix, soft theorems, and so on. But something that seems to be emerging is that the celestial formalism, writing everything covariantly on the celestial sphere, is very powerful. Indeed, in the last 2 weeks, we found that the positive helicity symmetries associated with positive helicity soft gravitons all organize themselves into a W infinity algebra. That would have been very hard to see in a Hamiltonian formulation. And solving this problem is step 0 for flat holography. The first thing that happened in ADS-CFT was the identification of the bulk symmetries of quantum string theory in ADS with various boundary field theories. And so the first step in developing a holographic correspondence is understanding what the symmetries are. Now, this is the real world. We're not assuming string theory either. I'm stressing both of these are bottom-up things. And so there are a plethora of experimental predictions which we should make and then persuade or interest our experimental friends in verifying that are associated with the infinite tower of conservation laws associated with these symmetries. The first of these is already underway, the detection of gravitational memory. So typical of the experimental consequences of these symmetries is that they're conservation laws that relate some collection of numbers from ingoing data to outgoing data and to some other collection associated with the outgoing data. And part of that data will be the memory, the gravitational memory, the displacement. Measurement of this is already underway at LIGO. Estimates of time are on the order of 5 years before they get this data for us. That's far from the end of the story because there are many more symmetries. So the subleading soft graviton theorem, which is related to conformal symmetry or superrotation symmetry of the celestial sphere, also has some asymmetry associated with it, so-called spin memory. And the LIGO team has talked somewhat about measuring that. It's harder. There's some proposal. I don't know how probable it is, but certainly at upcoming LISA, one might hope to measure this. Color memory. Now, color is confined, of course, so you can't see it out at infinity, but if you're fast enough, you can see it before confinement sets in. And there's a proposal to measure this at the already funded $1 billion electron ion collider. Now, interestingly, electromagnetic memory, which is in the same category of phenomena. There have been various proposals. I don't think any of these proposals were meant as existence proof of how you could measure it. Nobody has really put out a good proposal for a detector that somebody would actually build. But it's analogous. I should mention the magnetic Aronoff-Bohm effect has been measured, but in their original paper, there was also electric Aronoff-Bohm effect, which I think can be regarded as a subset of electromagnetic memory calculations. And there has been some work. It turns out to be very hard to measure because you have to keep phase correlations. And there's been some work, not very much, and they have not yet measured even the electric Aronoff-Bohm effect, but it's plausible. And there's more generally electromagnetic memory effects. And I say that it's also, I've found it to echo Nima. It's very stimulating to talk to experimentalists about how to measure things. It sharpens our thinking about what the nature of physical reality is and what the kind of theoretical structures we should look for. Now, both of those most of the work in celestial holography has been bottom up. That is, we've started with the laws of nature that we know and tried to deduce just from consistency and symmetry requirements what kind of holographic duality could exist in the real world. But it would be really interesting to have some top-down examples it's a duality that exists only in quantum gravity, so the natural place to look for it is string theory. There's the BFSS matrix model that is a dual representation of string theory in 10 or 11 dimensions that perhaps could be connected to some kind of celestial holography. There's also the n=2 string in 4 dimensions, which is a very simple yet rich theory that might have an interesting dual. Also, I'm very impressed by beautiful talks by Gopakumar and Gabriel, in which they kind of start with the world sheet, the string world sheet, and construct the boundary conformal field theory. And of course, they were working in they had a complicated interacting string world sheet. And here, there is a way, there are examples, and things like this were also done 20 years ago by Givyan Kutuzov-Seiberg, who did Nuva-Schwarz ADS3 cross S3. And to get pieces or all of the boundary conformal field theory out of the world sheet. And indeed, there should be some way that some sense in which the string world sheet in some approximation is the celestial sphere. That came out of work of Stieberger and Taylor. Finally, we'd like to characterize characterize constraints from the infinitely many soft conservation laws on information flow in and out of black holes. So we know that energy conservation forces quantum correlations between the microstate of the black hole and the outgoing Hawking quanta. They must be in a total state of the same energy. And now we have infinitely many conservation laws, which enforce infinitely many correlations between the black hole, microstate of the black hole, and the microstate of the outgoing Hawking radiation. This is the soft hair program. And in order to push this, see how far this goes, we need to be granted wish 1 first. We need to have a complete understanding of exactly what all these symmetries are and how they act. And finally, there's a very interesting analytic structure of the scattering amplitudes in the celestial conformal field theory. As Sabrina was mentioning, as a function of the conformal weights, we just have a series of poles at the negative integers on the complex conformal weight plane. It's writing things on the celestial sphere also bakes in the fact that there's a good UV behavior, so we don't have the freedom to be working in the swampland where things don't have good UV completions. And so we can, maybe a good place to put together all the many constraints that many people in many different fields have been talking about on the 4-point graviton scattering amplitude, and see what the most general form may be. And maybe this will lead us from the bottom back up to the top. Maybe, as many people have conjectured, some version of the string scattering 4-point function is the unique form. And so, okay, Tom is going to go next, but we'll take questions of any kind, and thank you for listening. I hope I didn't go too much over.
You are at 13, it's good. Thank you very much, Andy.
All right.
And let's pass it over to to Tomasz then for his half. Yeah, it's good. Please unmute. You do have to unmute yourself.
Okay, very good. Thanks, Pedro. And thanks, Andy. Well, quite a wish list. So here's how we got there, at least to some tiny part of it. So I will start with general remarks, then I will try to outline some roadmap to celestial CFT, and finally summarize on one page. But first of all, let me thank organizers for this wonderful conference and for giving the opportunity to say a few words about celestial holography. The first thing that I want to stress, actually, is special role on 4 dimensions in celestial holography. The whole story started from soft theorems, which describe infinite behavior of scattering amplitudes and the relation of those soft theorems to order ellipses of asymptotic symmetries. Now, the infinite singularities appear in any number of dimensions, but their physical interpretation is very different in higher dimension than it is in 4 dimensions. In higher dimensions, simply there's too little space to produce Bremsstrahlung. So there are, in other words, charged particles do not come surrounded by clouds of infinite number of photons. And similarly, in loop diagrams, when, for example, you look at the photon propagator, you see that loops are convergent as the photon momentum goes to 0 in higher dimensions, while they have logarithmic divergences. And for dimensions, actually, these divergences are responsible for the running of the coupling constants. So there's indeed a very special interplay of infrared and ultraviolet in 4 dimensions. Another thing is that only on 4 dimension, you have celestial sphere at null infinity. You have natural complex structure on which you can develop conformal field theory. And Lorentz symmetry is mapped into isometries of celestial sphere. In general, then superrotations become diffeomorphisms of celestial sphere. So only in 4 dimensions, you have these relation between fundamental symmetries on both sides. Okay, next thing is supersymmetry. Okay, so that's very simple story. When you know that supersymmetry algebra closes on momentum, in terms of celestial coordinates, momentum is not holomorphic. So there is no obvious separation between left and right. So even supersymmetric theory, you do not expect to have left and supersymmetries for left and right movers. So in celestial holography, supersymmetry does not play as fundamental role as it does in superstring theory. Okay, so now what about strings? As I mentioned before, there is no obvious decoupling between Z and Z bar between left and right movers, but celestial amplitudes with gravitons are ultraviolet divergence. And actually the degree of this divergence grows with the number of external gravitons. So the only way to have gravitational celestial amplitudes is in a theory in which you have exponential suppression at high energies. And here, of course, comes string theory, in which this with soft ultraviolet behavior, which is actually for 4-point functions, is controlled by Grossman saddle point. There's a similar limit for celestial amplitudes in which some conformal dimensions go to infinity. And in this case, this Grossman saddle point links the vertex position to the kinematic variable of the celestial sphere. So in some way, string world sheet gets spun to celestial sphere. And I suspect this relation is actually valid not only limit, but there is some deeper relation between strings and celestial holography. So to summarize this part, we start off on the right foot in 4 dimensions without supersymmetry and some very interesting relation to strings. All right, so here is what can we do in order to identify this celestial conformal field theory. The goal is to describe 4-dimensional physics as 2-dimensional conformal field theory. So the first thing to start, obviously, is perturbative Young mills, which we know very well, amazing progress over the last few years. And reconstructing this underlying conformal field theory is essentially a type of a detective work. So that explains my figure here, which is my best attempt to imitate Andy's artwork. I even do not dare to imitate Sabrina, who is beyond my abilities. So as any detective work, it consists of office work, which is identifying connections, motifs, symmetries, and this beautiful work that Sabrina mentioned on celestial diamonds of Sabrina and Apum and Trevisane go exactly in this direction, as well as this recent mysterious work of Andy about the relation to W infinity algebra. All this will help us in identify this conformal field theory. What I want to focus here of another aspect of the detective work, which is called field work, like would be normally identifying, trying DNA samples, like cups and so on. Here, we want to look at the amplitudes and to understand what's inside and understand the content and to understand celestial amplitudes as conformal colorators and see the content by exposing conformal blocks. Now, to do that, what you do, you start with celestial amplitudes, as Sabrina explained, and interpret them conformal field as celestial conformal field correlators or primary fields. Now, the basic building blocks of conformal field theory are 3-point functions. Now, here you hit the first obstacle, because on shell, 3 gluon amplitudes vanish due to kinematic constraints. So, well, one can try to change it by modifying space, the metric signature to comma 2, that replaces celestial sphere by celestial torus, that changes essentially the nature of the scattering problem. So I won't go here into that, but I want to just move to 4-point functions. And as you know very well, they depend just on the cross ratio of the 4 points. Now, they are related to kinematic variables. They are related to 2 scattering angles. One of is just regular scattering angle, and the other one is the angle that measures the planarity of events. And of course, 4-dimensional scattering, due to moment conservation, not 4-dimensional, 4-particle scattering events are planar. So what one finds that this 4-point correlation function vanishes everywhere except on the real axis. Actually, as you see here, it's a distribution valued, so it is not a typical conformal field theory correlator. So seeing that, you can do 2 things. You can just take it as it is and try to perform conformal block decomposition, or what we did in our recent paper with my collaborators, including my student Benzu, who will be graduating next year. We extended this 4-point correlator to the whole plane by performing something which is called shadow transformation. And then you can proceed like in textbooks, perform conformal block decomposition. And as a result, you find an infinite number of conformal blocks with various spins and various gauge group representations. So you find really an infinite number of Verma modules. So this is not a minimal conformal field theory. It's hopefully it's not maximal. Hopefully it's something relatively simple. And actually, in order to really figure out what it is, one has to want to think more about several open problems. For example, one need a more refined relation between the amplitudes and conformal field theory correlators. One has to understand the role of 4-dimensional kinematics in 2 dimensions. One has to understand the spectrum of conformal blocks. All these are other technical problems. So just I want to wrap up with, again, some more general remarks. So as you see now, celestial holography describes 4-dimensional physics in the framework of 2-dimensional conformal field theory on celestial sphere. It builds upon some very interesting and quite recent developments in general relativity amplitude program, and conformal field theory. From generativity, it takes symmetries of asymptotically flat space-time where we live. From amplitudes, here we take gluon amplitudes as you measure them at the Large Hadron Collider, and it puts everything in the framework of conformal field theory that we all know and love from string theory. So it is a win-win situation, and I'm sure that Andy will get his wish list sooner than he thinks. Thank you.
Thank you very much. You are perfectly on time. Thank you very much, Thomas and Andy, for a beautiful setup. So I remind everyone, please raise your hand, wave if your comment is related to what's being discussed right now. And if your internet allows, please turn on your camera. It's always much more fun to see each other. So Thomas, maybe you could stop sharing so we can have this gallery mode and we can see everyone's face. Perfect. Okay, so let me start with Shuheng, that I think in these particular discussions has been very quiet so far.
Hello, hi, hi Andy and Thomas. Thanks for the very inspiring presentation. So I want to follow up on a question raised by Simone earlier at Sabrina's talk about crossing symmetry. So celestial holography relates scattering amplitudes to Euclidean CFT correlator. Now, crossing symmetry in amplitudes is very subtle, as beautifully reviewed by Sebastian last week. On the other hand, crossing symmetry in Euclidean CFT is rather straightforward, just follows from microcausality. So I was wondering, like, if this is an interesting question, like, how much can celestial holography teach us about crossing symmetry, and how should I translate crossing symmetry from one side to another?
May I answer that? In order to do that, you have to have the correlators which are defined on a whole complex plane. So I think that the best way to go is to extend them in some way, and this can be done by using the shadow transform. And then you can start talking about relating different channels. There is here additional complication compared to usual CFT, that you have incoming and outgoing states, which are represented by different primary operators. Okay, so, but still, I think this can be done, and that's what actually we are working on.
Maybe I could comment too. Just first thing, we don't know. It's beyond what we've understood so far. The second is there's 4D crossing and there's 2D crossing, and they're related but different. And the third is that there are various singularities in this subject, and the natural way to deal with them seems to be to do what has been done uniformly pretty much in the amplitudes community, which is continue to 2-2 signature. And in 2-2 signature, null infinity has only one component. And so it's not like in 3-1. And so I think crossing must also be trivial in 2-2. Those are comments, not an answer.
Let's go to Mohab.
I'm wondering whether you can apply this program for not the field theory amplitudes, but for the string theory amplitudes. So for example, you mentioned the n=2 string, Andy, and there the string amplitudes are known. And so one could imagine trying to understand what celestial holography says and whether it describes the bulk string theory as a conformal field theory on the, well, it's not a sphere in this case because of the signature, but on the, let's say, in generalized sense on the celestial sphere.
Tom's written the only papers on this subject, so why don't you take it?
Sorry?
Tom, do you want to take?
Okay, all right. Okay. So what we started from really 4-point scattering amplitude, as we have from open string theory. And then you construct celestial amplitude, and you see a nice thing that indeed you have control, you obtain something which makes sense because you have exponential suppression at high energies. So you obtain celestial amplitude, okay, which graviton amplitude, anti-graviton amplitudes. And then, of course, you can think in this case, what is the underlying conformal field theory? Okay, so that's what you want to do.
Yes, but can you identify what the conformal field theory is, for example, for this?
No, we go in, even without strings and kind of Young-Mills, we still don't know what it is, but I think we are very close to identifying it.
Sorry. I think Gabriele's comment might have a comment which is related. Yeah.
Yeah, I think I have a comment which is related. Hi, Tom, and hi, Andy. Nice seeing you again. The point is, it's about unitarity, and also it's about the 4 graviton amplitude. Stringy gravitons or point-like gravitons, doesn't matter. I want to remind you that the high energy behavior at fixed angle is not given by the Gross-Mende saddle point, which is a complex saddle point and leads to an exponential vanishing of the amplitude, is given by the iconal in agreement with the fact that there is gravitational deflection. In perfect agreement. This goes back to the work of Toft, Amati, Cefaloni, and myself, Muzinich, and Soldate. So I don't think you can use for the high energy limit the Gross-Mende formula. The second remark is about unitarity. Again, unitarity is evident at large impact parameter or large angular momenta in the iconal approximation. And so my suggestion is, why don't you look at the amplitudes at fixed angular momentum and energy instead of fixed t and s? Because this is in angular momentum that unitarity is diagonalized. So can you generalize your connection to celestial amplitudes to amplitude defined at fixed angular momentum?
So does someone want to take up on this?
Comment and the question.
Yeah, Gabriele, let me ask you this. You see, I can take 4-point amplitudes as a function of SNT, yes?
Yeah.
And then I consider the limit in which the ratio is fixed, yes, as usual,
Yeah.
fixed angle. And I take the limit when SCNT goes to infinity.
Yeah.
And then I'm using Stirling formula essentially for gamma functions, and I find asymptotic behavior.
But that's not a unitary amplitude and not the leading term, because you have to sum to infinite genus to get the right result. We had a discussion in my discussion session with David Gross.
Absolutely. Just to say something very simple that Tom noticed, that the S over T, or T over S, I guess, becomes the conformal cross ratio on the celestial sphere. And so that's a nice simple relationship. And all that's been done at this point, yes, of course, it's true that at very high energies, the string scattering amplitude is not the Gross-Mende. But you know what has been done so far, there's only 2 papers on this, and I think it should be a very rich subject. There's only 2 papers on this, the relationship between, or maybe really only 1 paper, the relationship, you know, the celestial version of the string amplitudes, and all that was done, I'm not on any of them, all that was done was to, take the Mellon transform of the amplitudes and look at the analytic form and verify that it had the pole. Well, later it was verified that the poles were in the right places on the negative real axis. And it was enough that they fall off exponentially. They don't have to fall off to make them well defined. They are well defined the Mellon transforms are well defined at string tree level, even though it's not the black hole pair production fall off. But I think there should be some nice connection between, the operator product expansion and the celestial conformal field theory and the operator product expansion of vertex operators on the string world sheet, maybe using the kind of tools that Hirose and Wan used when they looked at strings in SL2R at the vertex operators, took the vertex operators to the boundary. So there's a world of stuff to do here, and there's just one paper.
Yeah, no, just to finish, I will be brief. I mean, what I wanted to say is that there is a lot of results, as you know, in the two-body problem in GR, even in the ultra-relativistic or massless limit. We know the answer up to 2 loops. So we know how things go at large angular momenta or large impact parameters.
Yeah.
And it's perturbative, it's not vanishing exponentially, the amplitude is there, healthy. So I think one thing you could certainly do first is to translate all those results in your language and see if they teach us something. On the other hand, if you want to go to the black hole formation regime, then you better work at small impact parameters, smaller than the energy in G Newton units of the collision.
Yeah.
And that's why I was suggesting that you look also at that dictionary.
Yeah.
From angular momentum to your variables.
Great suggestions.
Atul?
I wanted to ask Andy if, this is probably a slightly technical question, but in your W infinity paper, could you explain the role of the light transforms in the W infinity story?
Well, a little bit black magic. So which I hope we'll understand in the coming whatever, but there was a Monica and Alfredo and Mina and I worked out the algebra of all the not just the leading soft graviton theorem, but once you get to the sub-leading, you find that they commute them and you have more and more currents and you have an infinite tower of currents. This infinite tower of currents had been found by other methods, Hamada and a couple other papers. There's more and more soft theorems that involve higher and higher angular momentum. And we constructed the algebra, and it was pretty complicated. And then I noticed that, but we wrote it down in closed form, had a lot of gamma functions in it. And I just noticed that if you redefine the generators in a way that is not covariant under the right-moving SL2R, the whole tower dramatically simplifies, and it's just W1 plus infinity. And that redefinition is essentially a light transform on one side, but it's not a very familiar light transform because the representations that appear are integers. The original representations that appear are integers with negative weights. That's one of the features of celestial conformal field theory, is that they don't have the usual positive real weights. And so they're actually finite dimensional representations. So it's the same formula, but looks a little different because of the integer weights. I just wrote it out in modes. I didn't write it as a light transform, but I think it is the light transform. And And when you do that transformation, then everything simplifies dramatically. And also the gluons are in irreducible representations of the W algebra too. So it's clearly a big technical simplification. And there are also hints of W algebras in the n=2 string. And so we thought maybe this could make for some connection between the, with n=2 string theory.
Yes, this is in some sense the symmetry algebra of self-dual gravity, or self-dual Yang-Mills probably as well. So in some sense, is the conjecture here that we are just seeing the, since we're only doing the positive helicity OPEs here, are we somehow just seeing the infinite dimensional symmetry algebra of the self-dual sector?
Well,
between amplitudes?
The shamelessly wild conjecture with very little evidence would be that, yeah, these currents are all that you have in the self-dual gravity, and that the dual of the holographic dual of self-dual gravity is some two-dimensional W theory, and its quantization would be given by, as Hirose and Kumran showed, its quantization would be given by the n=2 string, but a lot could go wrong.
Thanks.
Kevin?
Yeah, just to follow up with what Adam said, it seems these algebras, like the W infinity algebra, appears in a very simple way from Penrose's nonlinear graviton construction, which is, of course, closely related to the n=2 string.
Right. That's the same thing. That's the same appearance of W infinity. And so the question is whether that W infinity is the same as the W infinity that appears in the.
So I just wanted to clarify one point. So if you were to build the algebra from a nonlinear graviton, what you would find is some very big chiral algebra. But if you looked at the Lie algebra of conformal primaries, that's W infinity. So that the actual chiral algebra is even bigger. Would you, is this what you found too?
Are you alluding to the fact that the chiral algebra is the wedge, is the Ketz-Moody algebra of the wedge algebra of W infinity?
Yes, I think so. It's like, it looks like loops in W infinity.
Right, so there's that, but then in the quantum theory, you have the enveloping algebra of that algebra.
Exactly, yeah.
I've just learned about all this stuff in the last week. There's a beautiful, my students are reading it and helping me with it. There's some beautiful papers by Chris Pope from the early 90s. Yeah, and this also happens in ordinary two-dimensional gravity. I guess, you know, Polyakov did the light cone quantization of two-dimensional gravity, and there he has an SL2R current algebra, not a Virasoro algebra. But we know that 2D gravity, we usually think of it as a Virasoro algebra, but it's all consistent because the enveloping algebra of the SL2R current algebra contains the Virasoro algebra.
Like what made me excited about this stuff is these algebras are really close to stuff that Davide and I found when we were studying holography for topological string. And also, there's a full paper of Edward from the early 90s, where he studied the C=1 string, I think.
That also has W, the same algebra.
Exactly, it's W. It's like symmetries with a three-dimensional cone instead of a two-dimensional cone.
Yeah.
Yeah. So this is what made me convinced that thinking about topological strings and twistor space, holography for it would be a good setting for the story.
Well, certainly topological theories like self-dual graphs, I don't know whether you call that topological or not, but topological like theories are certainly prime hunting grounds for theories where we could actually really construct a celestial dual. Yeah.
Let me go to Ashok.
Yeah, so I have a somewhat general question that whether it's in string theory or any theory of gravity, once you go to loop amplitudes, the S matrix becomes infrared divergent, right? And the question is, how will this affect the celestial correlators? So take the 4-point S matrix and it gets infrared divergent at one loop. How will it show up in the celestial correlator?
Okay, I guess I'll take that. I think the whole story of infrared divergences, divergences has a very nice picture in the celestial framework. Basically, infrared divergences appear because we weren't careful about imposing the conservation laws, and they appear when they set all amplitudes, which are basically all Fox-based amplitudes, set them to 0 when you exponentiate the infrared divergences, and any amplitude which doesn't violate the conservation laws, which is kind of baked into the celestial conformal field theory formulation, can be non-zero. And so that, but amplitudes which don't violate the conservation laws, have some kind of dressings, and the dressings can be understood as insertions of Goldstone boson fields, as we discussed in detail in Arcani Hamed, Pedro Clario, and myself. So I think the infrared divergence story is, there's still more to understand about it, but I think it works nicely in this.
Does that mean that one can now go backwards and try to define S matrix appropriately, which is infrared finite? Starting from
yeah, so of course, Fadeev and Kulish told us how to define infrared finite S matrices. The one thing that they missed is that the dressing for an incoming particle doesn't need to be in the incoming state. It can be in the outgoing state. You can move the soft particles from the in state to the out state. So Fadeev Kulish seemed weird because, of course, we don't dress. The LHC doesn't have, a little dressing shop where all the protons have to get dressed before they enter into the beam. So in that context, the dressing goes to the outside. It's the Cherenkov rate. It goes out. But having that dressing come out in the out state through the same sort of algebra, and this is, I guess, was proven by Okori, and we worked out the first order, but Okori, I forget the second author on that, proved it.
Choi.
Chong? Yeah.
Choi, Sang-Min Choi.
Yeah, so I think that the story of infrared divergences works nicely.
I'll soon go to the veterans. Thank you for your patience, but first one more from Igor.
Oh, hello, thank you. Can I say now?
Yeah.
Speaker? Okay. The W infinity algebras, looking very much like the Kac-Motte algebras, to me, the natural method for quantization is the Balatin-Vinkovitsky method. So have you studied the BRST cohomology in order to quantize the theory, meaning celestial holography, from a BRST cohomology? And the other question is, this algebras also appears if you generalize to the celestial sphere with punctures, or even the celestial torus or Riemann surface with more moduli parameters. So these are, as I can articulate my questions without taking much time. I am sorry. Thank you.
I guess I'll take that. So we haven't studied, so far, all this discussion is tree level. And the hope would be, that you get the quantization of little w infinity, which seems to have a unique one parameter family of big W quantizations. And it was very hard to see. And one of the nice things about, which has all been worked out for us, one of the nice things is that it was very hard to see how this tower of soft theorems, we know that there's quantum corrections to the subleading soft theorem and the sub-subleading soft graviton theorem, was very hard to see how you could deform this structure and still have a closed algebra before we understood that it was organized into little w infinity. But the problem of how you deform big W infinity was already solved in the early 90s. So the hope would be that that little w infinity gets deformed in big W infinity in the quantum theory, but that's going to,
if I may, what motivated my question is that you may want to abelianize. I am sorry if I am spelling things correctly. My English is very bad. Your algebra is a very powerful method to do quantum field theory for more generic non-abelian field theory. So have you thought how to abelianize the W infinity algebras? And my final question would be, the celestial torus that you have proposed, have you thought about generalizing them to more general human surface?
Maybe before passing back to Andy, maybe we could go to Kevin, because I think Kevin was waving with respect to your first point, and then we'll pass back to Andy.
Oh, I am sorry. I have forgotten about the hands.
No, it's okay. Don't worry. Don't worry. It's the relaxed part of the meeting. Don't worry.
Sorry, I just wanted to make a little comment about Andy's suggestion that one should use, because as we were discussing, the chiral algebra, or say the mode algebra, is much bigger than what is normally called W infinity. It's more like loops into W infinity. And quantization of that much larger object is really quite a challenging question. And my impression from studying anomalies for holomorphic field theories is that it doesn't always work. There are obstructions to finding a good quantization related to anomalies in the topological string. So my concern is that this is where one might run into difficult issues.
Maybe let's move to Shi, that we have I still have a few questions in line.
Hi. My question is closely related to what Ashok was asking, but I want to sharpen it a bit further. What is our expectation on, let's say, in a quantum gravity theory for the asymptotic Minkowskian spacetime? Do we actually believe that there's a mathematically well-defined S matrix of gravitons in the sense that it's a unitary operator acting on the Hilbert space? And if so, can we exhibit a countable orthonormal basis of that Hilbert space? So, I mean, I understand that there could be other kind of infrasafe observables. I want to ask specifically about the ordinary notion of S matrix. Can that actually be made sense in this context?
Remember, anyone can take up on such questions. Just wave or something.
If I can follow up then,
let's now give some opportunity for more new people to chime in. I'm trying to.
Of course, I
don't really know. Maybe somebody else could.
Maybe. My impression was that this may not have been established, but even just the expectation. Did you think it exists or does it not exist? I don't even know what the expectation is.
I think the expectation is that there is a unitary S matrix.
And acting on what Hilbert space? That's the question. That's also part of the question.
Well, the Hilbert space probably will have to have these dressed states.
Well, that's the part I don't understand. Are you saying that it's spanned by a countable orthonormal basis of dressed states? And if so, can we actually write it down and argue that it's unitary? Because to me, you know, the most naive problem is that, you know, because the infrared issue below a certain energy, below any finite energy, naively will write down an uncountable basis, and the naive calculation will tell you all the S matrix elements are 0. Now the question is there some clever basis in which the S matrix is actually unitary, and we can apply what we normally think is true for the analytic S matrix to the setting?
Yeah. Are you happy with perturbative unitarity, or you are you want to know in the black hole formation regime?
I would be happy to know the answer at perturbative level already.
I think that we see no signs that unitarity breaks down.
No, but there's infrared divergence.
Infrared divergences, you know, since Weinberg 65, that they can be coped with. Precisely like Andy.
That's not a reason. No.
You don't have to, let me finish. You don't have to dress the initial state. You only have to dress the final states.
The usual textbook resolution of infrared divergence is not at level of the S matrix element. It's a level of the scattering probability. That is fine, but what I'm asking is whether there's a unitary operator acting in the Hilbert space. That was not the usual textbook resolution. So I don't understand that statement.
Or you do it with finite epsilon, and then you prove that for all epsilon there is unitarity.
I think you have to take into account vacuum degeneracy.
Well, that's all part of the question.
In the sense that you explained, Andy, that vacuum degeneracy, if it is spontaneously broken, you can interpret the graviton as the soft graviton as the Goldstone boson. So if you dress your final state by gravitational radiation, I have seen, I mean, I have done many calculations, and people who do the scattering problem in GR. You know, your question also refers to the collision of two black holes. I mean, do you expect it?
Let me clarify. You know, the S matrix elements themselves are not directly physical observables. I mean, I'm not saying that there's any physical contradiction. You know, the actual observable scattering probability, inclusive scattering probability, there's absolutely no problem. What I'm asking is whether the mathematical object of S matrix as unitary operator on the Hilbert space actually exists, and that's not clear to me.
Well, you have to define your Hilbert space.
That's exactly my question. How do you define that Hilbert space, and whether you can exhibit a countable orthonormal basis?
But just so that we can still move on, but I saw that Simon wrote something in the chat, so maybe you can check there. But now let's maybe move to Eva.
Sorry, my question is a little orthogonal, but you'll see why it's related. So there's another approach to doing non-asymptotically ADS holography, which is TT bar-like deformation. So the TT bar deformation itself gives you addressed energy levels which agree with a finite patch of ADS, and then you can change the deformation in well understood ways to get the addressed energies to agree with the quasi-local energies of patches of other types of spaces. So it seems interesting to ask if one could do that for the flat space case. And if so, how would it relate to this approach?
Wait, you want to do a TT bar deformation of what?
So the way it works is you start with a CFT, which has an ADS dual. You do a TT bar deformation, and that brings in the boundary and gives you a patch of ADS that's finite. You can get down to where it's flat, and then add a deformation that, say, goes back out, but with a different geometry. So the way it works for de Sitter is you add not just TT bar at each step of this deformation, but you add a cosmological constant. And since it's a differential equation for the deformation, the cosmological constant enters into the stressed energy and enters into the dressed energy levels. And then, but in that way, you build up a calculable set of dressed energy levels, which agree with the Brown-York energies of a patch of space-time of different geometry than the original ADS. Okay, so it's a long trajectory from the CFT through this generalized theory space to a theory whose energy levels agree with those of a different bulk geometry. And people have mostly applied this to ADS and then to DS with flat space in the middle. So it's interesting to ask if when you do that for flat space, go all the way back out, you land on something that would give you a way to identify this dual theory. It's a very different approach. It has its own set of questions and wish lists and so on. But it is an approach to holography beyond asymptotically ADS, which is under development. So I was wondering if it has any relation to yours.
You want to use this for a top-down construction of a dual control, of a dual field.
Yeah, exactly. It's a way of tying it to some known dual and deforming the boundary theory as you deform toward the geometry you want. And it involves interpolating in the theory space defined by Zalbaldicus and others, involving TT bar deformations and their generalizations. So for the sake of discussion, I'm just bringing up this other approach to defining holography in non-asymptotically flat spaces, and I think non-asymptotically ADS spaces. And I think it might be interesting to connect the different approaches.
I have a suggestion. I suggest that we thank Andy and Tomasz for a beautiful discussion. And
Thank you.
I encourage everyone to, I think we should go to testing the share screen for